Kruskal's algorithm is a minimum spanning tree algorithm which finds an edge of the least possible weight that connects any two trees in the forest. This means it finds a subset of the edges that forms a tree that includes every vertex, where the total weight of all the edges in the tree is minimized. If the graph is not connected, then it finds a minimum spanning forest. This algorithm first appeared in Proceedings of the American Mathematical Society, pp. 48-50 in 1956, and was written by Joseph Kruskal. Other algorithms for this problem include Prime's algorithm, reverse-delete algorithm, and Boruca's algorithm. Description: create a forest F, where each vertex in the graph is a separate tree. Create a set S containing all the edges in the graph. While S is non-empty and F is not yet spanning, remove an edge with minimum weight from S. If the removed edge connects two different trees, then add it to the forest F, combining two trees into a single tree. At the termination of the algorithm, the forest forms a minimum spanning forest of the graph. If the graph is connected, the forest has a single component and forms a minimum spanning tree. Pseudocode. The following code is implemented with disjoint set data structure. Kruskal. 1a equals 2 4 arc VGV. 3 make set 4 4 arc ordered by weight, increasing. 5 if find set 6a equals a. 7 union 8 return a complexity, where e is the number of edges in the graph and v is the number of vertices. Kruskal's algorithm can be shown to run in O time, or equivalently, O time, all with simple data structures. These running times are equivalent because E is at most v2 and is O. Each isolated vertex is a separate component of the minimum spanning forest. If we ignore isolated vertices, we obtain VE plus 1, so log V is O. We can achieve this bound as follows. First, sort the edges by weight using a comparison sort in O time. This allows the step, remove an edge with minimum weight from S, to operate in constant time. Next, we use a disjoint set data structure to keep track of which vertices are in which components. We need to perform O operations, as in each iteration we connect a vertex to the spanning tree. 2. Find operations and possibly one union for each edge. Even a simple disjoint set data structure such as disjoint set forests with union by rank can perform O operations in O time. Thus the total time is O equals O, provided that the edges are either already sorted or can be sorted in linear time. The algorithm can use more sophisticated disjoint set data structure to run in O time, where alpha is the extremely slowly growing inverse of the single-valued Ackermann function. Example: proof of correctness. The proof consists of two parts. First, it is proved that the algorithm produces a spanning tree. Second, it is proved that the constructed spanning tree is of minimal weight. Spanning tree: let be a connected, weighted graph and let be the subgraph of produced by the algorithm. Cannot have a cycle, being within one subtree and not between two different trees. Cannot be disconnected, since the first encountered edge that joins two components of would have been added by the algorithm. Thus, is a spanning tree of minimality. We show that the following proposition P is true by induction. If F is the set of edges chosen at any stage of the algorithm, then there is some minimum spanning tree that contains F. Clearly P is true at the beginning, when F is empty. Any minimum spanning tree will do, and there exists one because a weighted connected graph always has a minimum spanning tree. Now assume P is true for some non-final edge set F and let T be a minimum spanning tree that contains F. If the next chosen edge E is also in T, then P is true for F plus E. Otherwise, T plus E has a cycle C and there is another edge F that is in C but not F. Then T minus F plus E is a tree, and it has the same weight as T, since T has minimum weight and the weight of F cannot be less than the weight of E. Otherwise the algorithm would have chosen F instead of E. So T minus F plus E is a minimum spanning tree containing F plus E, and again P holds. Therefore, by the principle of induction, P holds when F has become a spanning tree, which is only possible if F is a minimum spanning tree itself.